Next, going to look at how does these seek time, rotation latency, and transfer time matters in some of the popular real disks. So Cheetah is a popular series of hard disk. UltraStar is another popular series of hard disk. Atlas is another hard disk. For each of these hard disks, on x-axis for random 4K request size, so that's my IO size, for which we are measuring these performance. The y-axis is disk head usage. So what we want to see is among these three categories, seek time, rotation latency, and transfer time, where the disk is spending most of its time, right? Ideally, it should be transfer time because that's the useful work that we are doing. The seek time and rotation time is just an additional work that we have to carry forward in order to do the transfer. But as we see from this figure, unfortunately, the world is not quite as fair as we expect. So the transfer time is proportionally very less compared to the time that we spend in rotating the disks, as well as the time that we spend as a seek time. As we see that this black portion for each of this disk, while we run 4 KB IO size, it's very less compared to the light green portion and the grayed out portion. So this gives you some idea of how to compare these different latencies. Now, as you know, that the discussion topics sometimes, most of the times, and all the times pops up within our lectures, right? Time for our discussion topic for this module. What you would be writing your discussion post on is how do you anticipate or what do you think about the trend that you would see between seek time, rotation latency, and transfer time when we increase this IO size. So here, this graph shows for trend for IO size 4 KB. When we increase the IO size from 4 KB to, let's say, 100 terabytes, a single IO of 100 terabytes. Oh my God, that will be a very, very huge IO. I'm not sure what we would be doing with such a big IO, but doesn't matter. Let's say that if we are upon increasing this IO size, how would the trajectory or the trend between your relation of seek time, rotation time, and transfer time vary? Will seek time increase or decrease? Will rotation time increase or decrease? Will transfer time increase or decrease when we increase IO size? Or upon increasing IO size, what happens to TC, T-rotate, and T-transfer? That's what you are going to think and write your discussion post on for this module. Continuing with our discussion of this of the topic on hard disk further. I would give you a moment if you want to write down the topic of discussion so that you don't miss. Back. So next, what we want to discuss is, now that we know some of the basic terminologies, components of what happens within the hard disk, some cool ideas that people came up with that led to the construction of our today's hard disk or the components within that. Now let's look into one of the very common question that I usually get when people talk about T-seek time, because we just talked about the seek time, rotation time, and transfer time. Now there is a very common or one of the important notion that average T-seek is equal to 1/3 of full T-seek. Now, full T-seek is for any disk to go from the innermost track to the outermost track. That's full T-seek. So what this equation is saying that on an average, the time that's taken to go from one track to another track, some random one track, let's say track, let's assume 2 tracks on this disk, track X and track Y. So on an average, the time that it takes to move from track X to track Y is just 1/3 of the time that it takes to go from outermost track to innermost track, or vice versa. Why is this? And how do we come up with this magical factor of 1/3, right? Does anybody have any clue, any idea, any thoughts? Well, 1/3 is really a magical notion in many components of storage systems. So I would encourage you to spend some thoughts into thinking, why would this be the case, or why it is the case in this equation. If you want to scribble down some of your math equations, it would give you a couple of minutes to do that. Coming back. So if you figured out the mystery behind this equation all by yourself, very well, you have a good grip on math, because it's just taking a basic assumption and following through the mathematical relation behind that. If not, let me help you to come over that one extra step, right? So let's assume disk as set of tracks from 0 to n. Now seek distance between, that's just my acronym for between, any 2 tracks X and Y, as we see in the figure, would be absolute value of x minus y, right? Because distance from x to y or y to x is going to be the same. It's still the seek distance from x to y. So absolute value. Now, average seek distance is nothing but sum of all possible seek distances divided by number of different possible seeks. That is equal to the sum of all possible seek distances. So average seek distance between any two track is this, we know that. And there are two tracks here, x and y. So x can be anywhere between 0 to n, y can be anywhere between 0 to n. So summation of y anywhere between 0 to n and x anywhere between 0 to n divided by number of different possible seeks. Now, how many different possible seeks can happen between the n tracks? That's n multiplied by n squared. Now, this summation equation could also be represented as an integral to frame it into a continuous problem as x integral of x from 0 to n, integral of y from 0 to n, x minus y dy dx, right? Everybody with me until here? So now it's only the step to solve the above equation. We have done the tough part. So let me leave the outer integral. We would solve by parts. Solving by parts is a technique in solving integrals. So we would say y from 0 to x, where x minus y dy, plus we would say y from another x to n, where now y is greater than x, so y minus x would make more sense, dy dx, we still have the denominator of n squared from the previous equation, right? We forgot it here. So we still have the denominator of whole this divided by n squared. Now this is equal to x equals to 0 to n. Solving this integral over here, we would get xy minus y squared divided by 2. I'm just doing the math of solving the integral, no magic. If you're not sure what's going on, please refer to how to solve an integral, right? Here we have y squared by 2, integral of y with respect to dy, minus integral of x with respect to y is nothing but xy. Again, the limits are from x to n. This whole dx divided by n squared. Now solving that, just placing the limits into, let's place the limits into these equations. If we place the limits x and y, few of the components you would see it gets cancelled. You could do on your, you could try doing that on your own, but because the terms get cancelled, you would, when you put the limit of 0, x and n, the terms that you end up with x would get cancelled, and then some of the terms would get cancelled, and then in the same way as we solve this integral for dy, we would do it for dx, the remainder. And finally, when we solve the do the integral for dy and put the limits of dy again from dx, again from 0 to n, same as what we did for y. It's a repeated steps, so I'm just skipping that. And getting to the answer, we will get n cubed divided by 3 for this integral over here, and we still have our n squared that's lingering with us since the beginning, right? So then this n squared in the denominator and n cubed will get canceled, leaving us n by 3. And hence this factor of 1 by 3 could be transported in generating a relation between the average seek distance and total seek distance, as well as average seek time and total seek